Hello, my name is Elaine Aguilar. I want to introduce you to the last project for Technolife, dynamic inductor power transfers for electrical vehicle charging applications. Many years has passed since Carl Benz patented the first automated tricycle back in 1886 and with the beginning of the automobile. This creation has been through so many phases: how to make it faster, how to make it more comfortable, how to make it accessible to everyone, and lastly, how to make it eco-friendly. But right now, we are facing a new challenge: how to make the electrical vehicles more attractive for people. It is not a secret how climate change has become one of the major issues that the world is facing right now. And for this reason, Tesla was created with a mission to accelerate the world transition to sustainable energy. In the last years, we have seen other companies following the Tesla idea, like this that you can see here, and creating their own electrical vehicles. But if these eco-friendly cars aren't available in the market and we can get it, why people still buying those cars? According with the survey that the company did, we have two major reasons. The first one is the higher price for the electrical cars caused basically because the large size of the battery. And the second one is the charging time for electrical vehicles that can take hours. But what if I tell you that we can help to do this battery smaller? What if I tell you that you can drive your car and not worry about charging or where you need to stop, because your car is gonna be charging all the time that you're driving? Based on this idea, this team was put together with the objective to create a dynamic wireless power transmission for electrical vehicles that will be implemented on the highways, providing an unlimited range for electrical vehicles without the plugging or stopping for recharging. How are we gonna make it? This system for electrical vehicles consists on the receiver pad mounted on the chassis of the vehicles and the dynamic charge area, which is this one right here, that is gonna be underneath of the streets of the highways. The biggest problems that we have right now for this implementation is present the high cost of the same one.
Hello, my name is Carlisha Tresalis, and today I'm going to talk to you about intended use / intended users. It is important to know the intended use because it helps us figure out things like how much wattage the track would need to charge a vehicle, or how long the track would be, or even how much will the track cost. There is so much to take into consideration, so let's talk about the intended users. So, we have to ask ourselves, who could our audience be? For us, it is someone who is conscious of the environment, people who already own electric vehicles, someone who is always waiting for the newest technology to come out, drivers, or even companies. As for intended uses, we have to think about how we use it will affect the specifications of our project. So, if it was something that would be widespread, as in like daily use, maybe we would need something that would charge at a higher wattage. But if it's something that's probably for a company, maybe we wouldn't need a higher wattage, or vice versa. That's all I have for now, so let's go to the background.
My name is Pedro de la Rosa, and I'll be presenting the background for electric vehicles for Team 15. Now, electric vehicles have become really popular in the last couple of years, and it's going popular across the market. And one of the biggest reasons for it is the energy efficiency of these cars are almost double that of the most efficient gasoline engines. They're much cheaper to maintain, they're safer for the environment, and they're much safer on the road than gasoline engines. But they come with one huge problem, and that is their charging time for the batteries. A typical gasoline engine, once you're out of gas, any station 2 to 4 minutes and you're back up and running for another 400 miles. On an electric vehicle, you're looking anywhere from 8 hours to half a day, depending if you have a long range battery or a regular typical battery for your EV. Now, there are a couple of products out there that have tried to tackle this issue. Tesla came out with superchargers, 250 kilowatts of power to charge the electric vehicle. And But even with this much power, you're still looking at an hour wait time whenever you stop to get to fuel up. And this creates endless lines, clogged systems, and who wants to stop an hour in the middle of your road trip to wait for your car to charge up? It's not practical. That's where ours comes in. And our design is an inductive power design where you just drive and it charges as you go. No need to wait, no stop, no wait times, no appointments, nothing. Another one is battery swapping, like swapping batteries on a controller. That's what they thought to do for vehicles, but it requires a specialized technician, requires appointments. It's a huge infrastructure. And simple infrastructure under the ground in different arrays, and as you drive it charges. No need for anything massive. It just works. It's a lot more efficient, simple, everyone could use it. And the other solution is home solutions, but this takes a day. Imagine waiting a whole day for your car to be able to drive for the next day. It's not practical.
Hello, my name is Eric Bello and I'm presenting for Team 15. I'll be covering the intellectual property and ethical consideration sections, which are important areas to consider in engineering design. Intellectual property covers patents, trademarks, and copyrights, although for our project, patents are most relevant. During our research, we found similar designs with active patents and selected 3 of them. The first one claims the use of transmitter and receiver pads with 2 couplers placed side by side with a 3rd coupler placed on top, overlapping the bottom 2. The second patent claims a test mode in addition to its normal power transfer mode and also foreign object detection. The third one is called wireless power transfer method, apparatus, and system. Avoiding infringement on these patents is important to prevent lawsuits. For the first patent, our design uses a bipolar layout of 2 overlapping couplers, which avoids infringing on the first patent. We avoid infringement on the second patent since our design doesn't have the test mode or foreign object detection like the patent's claims. Ethics must be considered in the design process and is aided by having a code of ethics to follow, in our case, the one from IEEE. Our ethical dilemma is if this technology is widely adopted, it could create a lot of waste that ends up in landfills. This dilemma presented itself and the code of ethics wasn't sufficient to solve it. Instead, we used the ethical theory model and determined the best solution was to inform customers of providers that would upcycle the parts of their old car sustainably, and help is offered in connecting both parties. The good life we envision is a future where synergy among sustainable energy transfer and productivity align, allowing for time saving and continuous moving from point A to B. So moving on to my next teammate, thank you very much.
Hello, my name is William Zek, and I'm going to present the final concept of our project. Here's the blueprint of our project, which is the transmitter's end here and the receiver's end. It will consist of a receiver pad, a receiver end AC to DC converter and the corresponding controller, a capacitor, a battery DC to DC converter and the corresponding controller, and some additional features it will have is a battery voltage level, power, energy storage, and battery state of charge for display. The power pad we chose was a bipolar power pad, or a BPB. It was the solution to increase the power transfer in the area. It's also less cost effective and more efficient for dynamic applications. The other 2 options we had were a circular structure or a DD structure. Circular structure was not effective. It was going to cost more. And DD was good, but after a while it starts to become unstable on the x-axis, and we can't have that. Here is the data for the primary power pad. It has all the values, so we can start making them. Here's the prototype in the program: coil 2, coil 1, the ferrite, and the shielding plate. Here's all the values, and it consists of the graph. with the density of the power. So in conclusion, my team talked about the project description, markability, problem statement and objectives, intended users and uses, in the background, intellectual property, ethical considerations, and the final concept. Thank you.